So welcome to lecture series on advanced geotechnical engineering, and we are in module 4 and discussing about the shear strength of the soils. So this is module 4 lecture 7 on stress strain relationship and the shear strength of soils. So in the previous lecture we introduced ourselves about the PQ space and discussed about the Mohr-Coulomb criterion in depth. Then in this particular lecture we will introduce ourselves to methods for determining shear strength, especially in the laboratory, by two predominant methods, that is direct shear test and triaxial compression method, and thereafter we will introduce ourselves to stress paths relevant to the triaxial compression test and the drainage conditions. So after having covered these contents, we will be looking into the triaxial behavior and the stress state and analysis of unconfined compression, unconsolidated undrained, and consolidated undrained and consolidated drained, and other special tests and drainage conditions. So we have several methods for determining shear strength in the laboratory. Predominantly they are like direct shear test and triaxial compression test, and then there are some simple shear test and plane strain triaxial test. Like that we have several classes of tests which are actually can be done in the laboratory for determining the the shear strength shear strength parameters of the soils under considerations, both in disturbed or undisturbed conditions or for the remolded conditions. And then we also have some methods for determining direct or indirect methods for arriving at the strength parameters based on some parameters which are actually measured in the field. So the different determination of the shear strength parameters can be achieved through laboratory or through field tests, and in the laboratory predominantly the direct shear test and triaxial tests are performed traditionally, and there are also some other classes of tests like direct simple shear test and torsional ring shear test and plane strain triaxial test. And for very soft soils, if we wanted to determine where the sample making is difficult, then in that case we have laboratory vein shear test. And if we also have a fall cone test where it also indicates the penetration of the cone indicates an interpretation of the shear strength measurement. In the field, when we are having a soft soil, when the sample pickup is very difficult, then vein shear test at different depths is also popular. And then we also have some pocket penetrometer tests, and pressure meter test will give the in situ properties or in situ elastic modulus of soil. And as we discussed the static cone penetrometer test, which actually gives the cone resistance and frictional resistance or shaft resistance, and with the by interpreting the shaft resistance and frictional resistance we will be able to get an idea about the shear strength parameters. Similarly, the standard penetration test, which is the resistance of the soil is measured by the SPT n value. So we have number of correlations which can give for different n values by their undrained cohesion or the friction angle of a soil. So most common laboratory tests used to determine the shear strength parameters C or phi in case of total stress parameters, and C dash and phi dash in case of effective stress parameters. So total strength parameters are called as C and phi, and effective strength parameters are called as C dash and phi dash, and they are basically the direct shear test and triaxial shear test. So let us look into the direct shear test, and it is also called as a shear box test, and this box can be square or circular in shape, and these box sizes are predominantly 60 mm by 60 mm, or we have 100 mm by 100 mm or 300 mm by 300 mm. So depending upon the size of the particles which are actually involved, and to prevent the scale effects, the sizes of the the direct shear boxes need to be adopted. and is also used to determine the soil shear strength and not the deformations. And the different sizes of the shear box can be used depending upon the grain size of the coarse grained soil, or the grain size of the soil under consideration, or soil like material under consideration. And the sample is loaded first and with normal stress, and then subjected to a shear force, so that the shear can be applied on a predetermined shear plane, which is actually induced, the shear is actually induced along the predetermined failure plane. So this method of testing also makes possible for determining interface parameters, like when we have got let us say that two different materials, let us say that pile interacting with the soil, or when we have got a retaining wall interacting with the soil, and if you would like to have the interface friction angle, then the particular material can be kept at the bottom, and a dummy block can be placed, and then the required interface surface actually can be put, and then the required soil which is to be interacted with the particular surface can be placed. So with that we can actually determine the interface parameters, and when we try to determine the interface parameters, then it is actually called as modified direct shear test, and with that we get CA in case if you are having a cohesive soil, then adhesion is actually measured, and then interface friction angle. So this direct shear test actually has got the method of inducing failure along a particular plane is used actually as a way for determining the interface parameters, or if you wanted to determine interface friction angle between let us say a rock and surrounding soil outcrop, then that can also be achieved through this particular method of testing. So this typical direct shear test configuration is actually shown here. It actually has got a shear box, and in order to this, to some extent tests can be performed with some drained conditions, but they are actually regarded as you can actually do, but not possible for us to measure any pore water pressure and other aspects. And here the configuration is that you have got upper shear box and lower shear box, and in order to induce to keep the failure plane at the the predetermined surface, the serrated plates are actually used at the base, and then these serrated serrations actually have to be perpendicular to the direction of the shear, so that the failure is actually induced along that predetermined failure plane. And in order to allow the drainage, you actually have the porous stones, and then we have the loading plate, and through this loading plate can go down or go up, so it is which is slotted here, and this actually with the lever arm arrangement we actually apply the normal stresses, maybe in the range of 25 kilopascals to 300 kilopascals to 400 kilopascals normal stresses can be applied. And then what it is done is that the shear force is actually applied as shown here, and with that the resistance offered by the interacting soil or soil surface is actually measured. So with that you will be able to get the shear stress versus shear displacement. So what when we apply the shear force, if this is the direction of force, and then there is shear force is actually generated and the shear displacement is generated. So when we do at different normal stresses, we actually get a set of curves for each normal stress which is actually performed, and then depending upon the type of the soil, whether it is a dense soil or whether it is a loose soil, we have the variations in the types of the pattern of the stress curves changes. Similarly, if you are having a undistributed sample, let us say a over consolidated soil or a normally consolidated soil, and the pattern of the stress distribution, the shear stress versus shear strain variation is subjected to change. So here the mechanism is that at the start of the test, what actually happens is that you have sigma n and sigma h. So these are the major principal plane is actually here, major principal plane is here and minor principal plane is perpendicular to this, and at the beginning of the test, when before the commencement of the test, on the failure plane, the major principal plane and the minor principal plane, they do exist, but when the test commences or during the test, because of the mobilization of the shear, and then those that particular failure plane can no longer be called as a predetermined plane over which the failure is being induced. It can no longer be called as the principal planes. So in that principal plane, in that case, then we have to see that there is a chance that in the direct shear test, the rotation of the principal planes can actually occur. And here in this case, the stress state at the end of the test is shown here. So you have got a normal stress, and then there is a shear stress which is actually mobilized. So this makes it actually not eligible to be called as a the principal plane during the test. And this is the normal stress remains constant for a particular sample of the test. So in this particular figure, the typical shear stress versus shear displacement for loose sand and medium sand and dense sand actually are given. So as can be seen that loose sand actually has got the continuously the hardening effect can be seen, but in case of a the medium sand and dense sand, and particularly for dense sand, there is a predominantly a peak is actually observed, and then once the peak stress is actually observed and there is a decrease in the peak shear stress with an increase in the shear displacement or shear strain. So peak shear stresses are noted down at each normal stresses, and then when we plot these peak shear stresses for each normal stress, what has been done, then what we get is that the tau sigma tau sigma space, we actually get the the Mohr Coulomb failure envelope. The slope of that Mohr Coulomb failure envelope joining all these tau 1, tau peak 1, sigma 1 and sigma n1, sigma n2, sigma n3, and that actually gives the the slope of line actually gives the the internal friction angle. And if it is actually intercepting at the tau axis, then that intercept is actually taken as the cohesion of a soil. So when we plot in the direct shear test, as we can see that here the vertical strain can be measured by putting a dial gauge, and the lateral movement can be measured by putting a in case for dial gauge or a potentiometer or LVDT. So with that, what will happen is that you will get shear displacement or shear strain versus vertical strain. So this vertical strain can be can lead to expansion, or it can be lead to compression. So what actually happens is that in case if you are having a loose sand, as can be seen here, it continues to harden. So in line with whatever we have actually observed for tau sigma, we can actually see that this undergoes a continuous compression. So in this case, the contraction actually takes place, but in case of dense and medium sand, for a given normal stress, what will actually happen is that initially there will be a compression, then thereafter what will actually happen is that, as been discussed, this was actually discussed in the previous lecture, that the soil particles ride on each other and then induce and make the the loading plate to move upward, because there is no other way the particles that actually can accommodate the disturbances which are actually created because of the shear. So in a way, what will actually happen is that there is a dilation, or in the sense that expansion in volume takes place, and this actually get suppressed with a decrease in particle size. And similarly, when we are actually having increase in the normal stress, the tendency of the dilation actually keeps on changing. So volume keeps on decreasing for loose sand, but in case of dense sand and medium sand, what will actually happen is that initially there will be a compression, and thereafter there is an increase in expansion of the soil takes place upon shear. So this actually phenomenon is actually attributed to the dilatancy effect, or it is also the slope of that particular line is also called the dilatancy angle. So as we said, and we can analyze or look into this as a saw blade analogy. So it can be seen that when a shear is actually applied along the saw blade, actually we have the movement actually can take place. So the apparent externally mobilized angle of friction on horizontal planes pi is actually larger than the angle of friction resisting the sliding, that is pi u, or in the pi u or pi I is equal to friction plus dilutancy. So the strength is actually nothing but friction plus dilutancy, that actually what it actually turns out to be. Now as we have seen that it can be possible that the soil can be in a very dense state, and the soil can also at particular situation that after a certain point actually where the shear can actually occur at constant volume, then that is actually called as critical, and when this actually attains at a constant volume, the no change in void ratio takes place, that is actually the void ratio at which no change in volume takes place, then it is actually called as a critical void ratio. And then when you are having a initially loose, then as we have discussed it, that these all loose pockets which are actually there, they get filled with the soil particles, so then that the compression actually takes place. So you can see this the orientation of the saw blade analysis is actually given in the downward direction, and here it is actually done in the upward direction. This actually shows that the riding effect, and this is also some depositing effect, like one particle will get jumbled into other particle. In a way what will happen is that there is a decrease in the volume takes place. So let us look into this interlocking and dilutancy phenomenons. When soil is initially denser than the critical state, where critical state is the place where no volume change occurs, which it must achieve then as particles slide past each other owing to the imposed shear strain. On an average they will actually tend to get separate, and the particle movements will be spread about a mean angle of dilation, that is called psi. And in a dense sand there is a considerable degree of interlocking between the particles takes place, and before shear failure can take place, this interlocking must be overcome in addition to the frictional resistance of the points of contact. In fact, the peak actually which is attributed in case of a dense sand samples is actually attributed to the interlocking effect, which actually results in the mobilization of the peak shear stress, and thereafter the softening actually takes place. So in a dense sand there is a considerable degree of interlocking between the particles, and before shear failure can take place, the interlocking must be overcome in addition to the frictional resistance at all points of the contact. So in this particular slide we can see that the variation of the volume increase for a dense sand and loose sand is actually given here. In this case of dense sand there is a contraction, in the case of a loose sand for a given normal stress we could see that there is an increase in volume takes place. So this is the slope of this line, that is d epsilon v, that is the change in vertical strain or volumetric strain to the shear strain. That is actually regarded as the angle of dilutancy. So in general the degree of interlocking is greatest in the case of very dense well graded sands and soil particles with which are angular in nature. The texture of the particles, if it is angular and rough, and there is a possibility that the degree of interlocking is the greatest, and basically in the case of very dense sand or well graded soil mix, and then the angular particles. And the characteristic stress strain curve for an initially dense sand shows a peak stress at a relatively low strain, and thereafter as the interlocking is progressively overcome, the stress decreases with increasing strain. So the characteristic stress strain curve for an initially dense sand shows a peak stress, that is what we have discussed, at a relatively low strain, and thereafter as the interlocking is progressively overcome, the stress decreases with increase in the strain. So the reason for having observed peak and then decrease in the stress value with an increase in strain is attributed to the breaking of that interlocking which actually was provided till that time, and then upon shearing, once it is overcome that interlocking, then what will happen is that there is a decrease in the stress with an increasing in the strain. So the reduction in the degree of interlocking basically produce an increase in the volume of the specimen. So the reduction in the degree of interlocking. So this particular reduction of or breaking of this interlocking results in the in increase in the volume of the soil specimen which is being subjected to shear. So, as characterized by the relationship between the volumetric strain and the shear strain in the direct shear stress. So, the reduction in the degree of interlocking produces an increase in the volume of the specimen, and during shear as characterized by the relationship between the volumetric strain and the shear strain in the direct shear test. Now, the term dilatancy is used to describe the increase in volume of a dense sand during shearing, and the rate of dilation can be represented by the gradient which is nothing but what we have said is that d epsilon v by d nu which is the maximum rate of the corresponding to peak stress. The angle of the dilation psi is nothing but tan inverse d epsilon v by d nu, and for a dense sand the maximum angle of shearing resistance pi max is determined from the peak stress is significantly greater than the true angle of friction. So, we have maximum peak friction angle that is actually determined at the wherever we have the tau peak is there, and when you pick up these values and plot the Mohr Coulomb envelope with normal in the tau sigma space, then what will actually happen is that the slope of that line which is actually having a peak shear stresses which is actually called as the pi max. And there is also true angle of internal friction, that is actually nothing but the frictional resistance offered by the individual particles, and for that actually it is pi u it is called, and that is pi mu, it is called pi mu. Mu indicates for the frictional, the sliding friction, and the difference representing the there is a difference between these two, between pi max and pi mu, and that is actually because the difference representing the work required to overcome the interlocking and rearrangement of the particles. So, pi mu is actually more than pi max, pi max is actually more than pi mu, and this is basically the difference. There is a difference between pi max minus pi mu. This basically the difference is attributed to the work done which is actually required to overcome the interlocking and the rearrangement of the soil particles. Then we said that when you have got initially loose soil sample, there is no significant interlocking takes place, and the particles always tend to arrange into the new position, and in the way that the soil undergoes a contraction upon actually shearing, and the shear stress increases gradually to an ultimate value without a prior peak and accompanied by a decrease in the volume. So, in case of initially loose sand, there is no significant particle interlocking takes place. So, that is the reason why there is no peak is actually observed, and the shear stress versus shear strain variation is actually that, and the shear stress continues to increase, and after reaching the at large strains it actually tends to become constant. So, in the case of initially loose sand, there is no significant particle interlocking to be overcome, and the shear stress increases gradually to an ultimate value without a prior peak and accompanied by a decrease in volume. But when soil is initially looser than the final critical state, then the particles will tend to get closer as the soil is disturbed, and the average angle of dilation is negative and indicating a contraction. So, the angle of dilation is actually negative, that is actually indicates a contraction actually takes place. So, let us try to interpret between pi max and pi mu and pi CV. Pi CV is the friction angle at constant volume, and CV indicates at constant volume. And so, in this particular slide, tau versus shear strain is actually shown here, and where for dense sand and loose sand the shear stress variations are shown here. As can be seen that the shear stress is actually maximum here, and then the peak is actually distinct peak is actually shown, and then there is a decrease in shear stress with an increase in the shear strain, and it tends to become in join with the curve, wherein when we have got the hardening actually takes place continuously for initially loose sand and becomes denser by virtue of shearing. So, this thus at the ultimate or at a critical state, the shearing takes place at a constant volume, and the corresponding angle of shearing resistance being denoted as pi CV or pi critical, it is called pi or critical friction angle, and the difference between pi mu and pi CV represents the work required. So this is actually, this gives the pi CV, and this actually require this somewhere here, somewhere here the this is due to the sliding friction, the sliding that is because of the frictional resistance offered by the particles in arranging into the into the denser configuration is actually is indicated with the phi mu, and here the difference between pi mu and pi CV represents the work required to rearrange the particles. In general, the critical state is defined identified by the extrapolation of the stress strain curve to the point of constant stress, and which should be also correspond to the point of zero rate of dilation on the volumetric strain stress curve. So this also corresponds to, so the void ratio at which this this particular phenomenon occurs, this is actually called as the critical void ratio, and this is the critical void ratio. So this is the the critical state is identified by the extrapolation of the stress strain curve to the point of the constant stress, and which should also correspond to the point of zero rate of dilation on the volumetric strain shear strain curve. Now now we said that at constant volume, when the friction angle is interpreted, then it is also called as critical friction angle or pi CV. And if the density of the soil does not have to change in order to reach the critical state, there is a zero dilutancy as the soil shears at the constant volume. But it is important to realize that a critical state is only reached when the particles have had a full opportunity to juggle around and then come into new configurations. That means that progressively this state is actually achieved, and if the confining stress is increased while particles are being moved around, then they will tend to finish up in a more compacted state, so that arrangement will not actually happen. Now among phi max and phi CV, in practice the parameter phi max, which is actually is called as a transient value and should only be used for situations in which it can be assumed that the strain will remain significantly less than the corresponding peak stress. So if for a given structure, when it is actually being designed, when the strain is actually when the strain is actually less than at which the peak stress is actually interpreted, then the pi max is actually can be recommended for use. So in practice, the parameter phi max, which is a transient value and should only be used for situations in which it can be assumed that the strain will remain significantly less than the corresponding to the peak stress. If however the strain is likely to exceed the corresponding to peak stress, if the strain is likely to exceed the corresponding peak stress, a situation that may lead to progressive failure, then it is actually a critical state parameter and pi CV is used. So when we need to use pi CV, when we need to use pi max is actually clarified in this slide. If however the strain is likely to exceed, the strain in the sense that induced for a particular geotechnical structure is exceeded that the corresponding to peak stress, a situation that may lead to progressive failure, then the critical state primarily parameter pi CV should be used. So here when we look into this for the interpretation of the direct shear test, and we actually said that when dense sands or over consolidated clays are sheared, they dilate. So when dense sands actually are over consolidated clays, when they are subjected to shear, they tend to dilate, and larger the particle size, greater is the dilation, and the decrease of the particle size actually decreases the tendency of the soil to dilate, and more Coulomb idealization implies dilation at a constant rate when a soil is sheared, and this is actually appear to be unrealistic. So when dense sands or over consolidated clays are sheared, they tend to dilate, and larger the particle size and greater is the dilation, and decrease in the particle size suppresses the dilation tendency, and also increase in the normal stress and increase in the war burden also suppresses the dilation tendency. Now let us look into the interpretation of the direct shear test results, and then we will try to look into some example. And here the peak shear stresses are noted from the shear stress versus shear displacement or shear strain curve, and each normal stress, the peak stress is actually when it is picked up and when it is plotted here, and the line joining this this envelope is actually resulted as a Mohr Coulomb failure envelope. And if it is a purely frictional soil and with negligible amount of fines, there is a possibility that the friction angle, the envelope can actually pass through origin. And important aspect we should remember is that while plotting these results, the tau sigma curves have to be on the equal scale, so that the proper interpretation can be done. So there will be like 1 or 2 or 3, basically minimum 3 are required, and if you are actually trying to do like say 5 normal stresses, and so you will actually get the 5 number of shear stress displacements, and a plot of the peak shear stress versus normal stress do give the shear strength parameters phi and c from the a particular soil. So we will able to get the c and phi for a particular soil from this curve. And further there is a way where we can actually construct the Mohr circles, because here in this case what we are trying to do is that we can actually construct the Mohr Coulomb failure envelope, and we know actually this particular point. So what we can do is that this point Mohr circle, Mohr Coulomb hypothesis actually states that when Mohr circle is in contact with the failure envelope, then that is the point where the failure stress, the tau failure shear stress is actually achieved at a particular normal stress. So here for sigma n1 tau f1 is the failure shear stress, sigma n2 tau f2 is the failure shear stress, sigma n3 tau f3 is the, so this is actually the dotted line which is actually shown is the failure envelope. And now with particular dropping a perpendicular to the sigma axis from the failure envelope, we can actually locate the center of the Mohr circle, and with this as actually a center, we can, if you draw a Mohr circle, then we will be able to locate major principal stress and minor principal stress. And from the known stress state on the Mohr circle, if you draw a line horizontal parallel to the sigma axis, it actually intersects at a point P, and that point is actually regarded as a pole, and from the pole when we join these points to major principal stress ordinate here and minor principal stress ordinate here, then actually we can get the inclination of the major principal plane and minor principal plane. And so when we draw the Mohr circle, we will be able to get the major principal plane and minor principal plane locations and the magnitudes of the stresses and the direction of the principal planes and all. So as can be noted, if you look into that, initially when the when you start the prepare the sample and then kept it for equilibration also, at the time when the no normal stress is when the normal stress is applied, when the no shear stress is applied, when we have got along the predetermined horizontal plane, you actually have the principal planes, but upon shearing and during shear test, actually in a case of direct shear test, the principal planes are subjected to rotate, and they rotate in the direction of shear, and the degree of angle of rotation of the principal planes is approximately regarded as equivalent to the friction angle of a soil. And so like this, when we do different normal stresses, and when you get register tau f2 and tau f3 the failure stresses, you can actually draw these Mohr circles, and these Mohr circles from here onwards. So the line which is actually joining to this parallel to this one, that is actually is nothing but the it indicates the failure plane, and this indicate when it is actually meets at the point say P1 here and it is joining here, then this is called the major principal plane inclination, and when it is joining to this particular point, that is called minor principal plane. So we actually can determine the angle of the inclinations of major principal planes and minor principal planes and their magnitudes when we know the stress state points at failure for sigma n1 and then tau f1 or sigma n2 and tau f2 and sigma n3 and tau f3. So this is the initial condition. It has been, as it been described here, initially when we actually have sigma n0, that is the normal stress, let us say a 50 kilopascals of normal stress is applied, and for a normally consolidated soil, when you take earth pressure at rest K0 as say 0.5, then in that case the horizontal stress which is actually there in the soil is sigma h naught is equal to k naught into sigma naught n naught. So 50 kilopascals into 0.5, let us say 25 kilopascals will be there. So when we draw that, when we have the normal stress sigma n naught, and this is called initial Mohr circle, and this Mohr circle is actually well below the Mohr Coulomb failure envelope, then we actually have discussed it that this Mohr circle is regarded as the stable condition. Then further, when with that same normal stress, when we try to induce the shear, then what will actually happen is that the Mohr circle actually generates the shear force, and with that what will happen is that the Mohr circle becomes like this. So with that what will actually happen is that you can actually get a point where it reaches to the failure. So that is actually during the test and before the failure. And so from here, if you look into this here, when you have this point at failure, so what we have discussed is that when you draw in order to locate this, and this when point is actually drawn, so this is the center, this is the center, and this is the radius. When you draw, when this is the radius, when you draw the Mohr circle, then you can actually get a Mohr circle tangential to the so called failure envelope, and then passing this point and this point, and then when you draw and locate a pole, then when you join it to the major principal stress here, then what you get is the major principal plane. So the major principal plane is here, and minor principal plane which is actually here. So these are the directions or inclinations of the minor principal plane and major principal plane. So let us consider an example wherein a direct shear test is actually run on a medium dense and sandy silt with normal stress of 65 kilopascals. At failure, the shear stress is observed as 41 kilopascals, and draw the Mohr circles at the initial and failure conditions and determine principal stresses at failure, and the orientation of the failure plane, and the orientation of the plane of maximum normal stress at failure, orientation of the plane of maximum shear stress at failure. So these issues can be addressed by the discussions whatever we had till now. So initially when normal stress is actually applied starting at the test, then the 65 kilopascals is actually located here, and when we locate with being a silty sand, and friction angle is actually given as 32 degrees. So when we take using Jacques formula, k naught is equal to 1 minus sin phi, and with that 1 minus sin 32 degrees is equal to, then it comes out to be around 35 kilopascals, and with that 65 minus 35, that as 30 kilopascals as the diameter, when you draw the Mohr circle, you will get the initial Mohr circle for the initial condition. Then it has been given as the failure shear stress is actually located at 65 kilopascals normal stress, at the normal stress is actually somewhere around 41 kilopascals. So what actually happens is that when you locate that point, and because it is given as silty sand and the cohesion is actually assumed to be 0, and then it actually passes through the horizon. So with that what we can actually get is that you actually have got tau sigma envelope, this is the tau, and sigma envelope actually here passing through this is the point which is actually at 65 and 41. So when the angle of internal friction is equal to 30 degrees, the slope of the line passing through the origin and point, that is 65 and 41, and then in order to find the center of the circle, with by dropping a perpendicular from here, then we can actually locate a point where it actually intersects the center. Then with this as the center and this as the radius, we can actually draw a Mohr circle, and that particular Mohr circle represents the Mohr circle actually becomes like this, and then because we have taken this as the radius, so it becomes tangentially here, and this particular point where it actually intersects sigma, and that is actually regarded as the minor principal stress. So in this case about 40 odd kilopascals is actually is the minor principal stress, and here sigma 1 is actually here about 140 kilopascals is the major principal stress. So we actually have located the Mohr circle and drawn the Mohr circle, and the theta, which is actually 45 plus 5 by 2, that is actually 45 plus 32 by 2, which is actually 61 degrees. Angle between horizontal and the line joining the center of the circle and point 6541 is 180 minus 2 theta, which is about 58 degrees. So that is actually here is indicated here. Now horizontal line is extended through point 6541 to the other edge of the circle, which actually gives pole, and the line drawn through the intersection points between the circle and normal stress axis gives the principal plane inclinations to the horizontal. So as we have discussed that when we draw this line from the point to this point and this point, we will actually get the inclination of the principal planes with reference to the Mohr circle diagrams. With that we will be able to get we can see that initially when the sample is actually just prepared, then we actually have got 65 degrees and about 30 odd kilopascals as the minor principal stress, but now the principal stresses magnitude has increased as well as the direction also changed in the direct shear test. So further in continuation of whatever we have been discussing, we can actually look into the another way of plotting the shear stress versus the shear strain data as the ratio of tau by sigma dash for a different sigma dash. When we actually take with increase in sigma dash, actually in this direction C actually has got lowest, B and A, then there is typical A, B, C plotted actually are shown, different sigma dash and same E naught. E naught initial void ratio is actually same for all the samples which are actually shared at three different normal stresses. Both maximum stress ratio and ultimate or critical void ratio decreases with increasing effective normal stress. Then the difference between maximum and ultimate stress decreases with increasing effective normal stress. So the value of the pi max for each test can thus be represented by a secant parameter, and the value decreasing with increasing effective normal stress until it becomes equal to pi CV. So because of this particular phenomenon, what actually happens is that at low effective stresses, we actually have the difference between the critical friction angle as well as the pi max, that is the peak friction angle. But when it actually has got the normal stresses actually increase, then the what actually happens is that the suppression of the peaks actually appear, and then predominantly the hardening actually takes place. Because of that, what will actually happen is that they merge to the pi CV axis. So you can see that at high normal stresses, high effective stresses, there is a beyond point B, you can see that there is a merging of these angles takes place. So this particular phenomenon is actually attributed to the decrease in the ultimate void ratio. So the both maximum stress ratio and the ultimate or critical void ratio decrease with increasing effective normal stress, and the difference between the maximum and ultimate stress decreases with increasing the effective normal stress, and the value of the pi max for each test can thus be represented by a secant parameter, and the value decreasing with increasing effective normal stress until it actually becomes equal to pi CV. So after having discussed the direct shear test, it actually has got first of all, the direct shear test is a simple test and actually allows to determine the strength parameters of soil very easily, and the failure plane is actually one to be noticed, that the failure plane is actually predetermined and very difficult to control the drainage condition. But however, to some extent what it can be done is that when you have got a shear box, and if you wanted to get to some extent consolidated and drained parameters, what it can be done is that the sample can be prepared, and particularly if you are having some silty sand or silt samples, the samples can be prepared either under remolded conditions or undisturbed conditions, and allowed to saturate under a particular normal stress over a period of time. Then the shearing can be done at very low strain rate, so that the stress, there is no generation of excess pore water pressures during the shear. So with that, with this exercise we can actually get drained parameters up to a maximum extent. Otherwise, basically the total strength parameters are actually obtained, and so in a way the pore water pressure measurement is actually difficult, and only the total stresses can be determined in this particular case, and shear stress on the failure plane are not uniform, as failure occurs progressively from the edge to the center of the specimen. So one thing we need to notice is that the shear stresses on the failure plane, they are actually not uniform, as the failure actually occurs progressively from the edges to the center of the specimen, and area under the shear and vertical loads does not remain constant throughout the test. So one more assumption, observation we have to make is that the area under the shear and vertical loads does not remain constant throughout the test, and the soil is actually forced to shear along the predetermined plane, and which should not actually necessarily the weakest plane. So if you look into that, we actually have imposing failure along a predetermined plane, which may not be the failure plane in the particular sample. In such situation is actually we are actually regarding as the failure to take place along a predetermined failure plane. And the another disadvantage or demerit which actually comes as far as direct shear test is concerned is the rotation of the principal planes, as we have seen that during shear the principal planes undergoes rotation in the direction of shear, and the angle of rotation of these principal planes is approximately estimated as the inclination of the failure envelope with the horizontal, that is the friction angle. And so these are the some disadvantages which are actually listed here, and the only advantage with the direct shear test is simple, and in case of sands is easy for the sample preparation. So another advantage is that the interface parameters, and this is actually where when you have actually got multiple interface layers nowadays, when we actually design a landfill lining system, when we wanted to have the sliding friction values, or in case of the reinforced soil walls, when we wanted to have a sliding friction between the reinforcement which is actually which is interacting with the surrounding soil, in order to get these parameters, or interface between a geomembrane interface and soil under different conditions, like without water or with with the presence of the water, in a number of cases actually where the interface characteristics can be analyzed, and this is actually becoming very handy as far as determining the use of the direct shear test is actually concerned. Now, as we said that the another way of determining the strength parameters is the triaxial compression test. In fact, the triaxial compression test is the first physical model test which actually wherein the in situ conditions are actually attempted to be simulated. So here this triaxial sample actually simulates, let us say that if you are having a soil sample collected from a certain certain depth, let us say at say 5 meters depth or 10 meters depth, and then the soil sample will be actually having a vertical stress and the lateral stress which is actually equivalent to, let us say, in equilibrium conditions it is k naught times sigma v, and with that what will happen is that it is subjected to these conditions. Now on these conditions, let us say that there is an increase in the vertical stress which is actually happening, and upon that increase in vertical stress, if you wanted to see what is the angle of the resistance actually offered by the soil, and that can be actually simulated by using this particular type of test which is actually called as a triaxial compression test. So this actually test actually has got one of the widely used tests wherein you can actually get have the parameters which actually can have well controlled drainage conditions. The soil strength parameters can be estimated very accurately, and mostly based for shear strength tests is suitable for all types of soils, and wherein you can actually do on very soft soil and not very soft soil, and where soil sample can be made to stand, and then also loose sand, dense sands. Yes, different techniques need to be adopted and it needs to be considered. And one important point we need to actually highlight is the L by D ratio. So in this case the L by D is actually maintained as 2, that means that length of the sample is always the 2 times the diameter. This actually one particular requirement which actually needs to be satisfied is that because of the L by D is equal to 2, what will happen is that the failure plane will remain within the sample length only. The otherwise if you are noticing whatever we are actually applying on the horizontal surface and along the this vertical plane, and these are actually regarded as the minor principal planes, and they actually remain as minor principal planes during the test and even the end of the test. So that means that in the case of triaxial shear test, whatever the limitation which we actually have said, the two major things, one is that the non-uniformity of the shear along the failure plane and induced failure plane and the rotation of the principal planes, those limitations are actually overcome very easily in triaxial shear test. And the typical sample diameters for the the sample specimen diameters for triaxial shear tests are the 38 mm, 100 mm and 300 mm, and 38 mm is generally used for the small samples, 38 mm diameter and 76 mm height, or there is also one more intermediate size which is actually 75 mm diameter and 150 mm height, or 100 mm diameter and 200 mm height, or 300 mm diameter and 600 mm height. In some special cases where we are actually having a large size particles, then even 1000 mm diameter or 500 mm diameter and 1 meter height, or 1000 mm diameter and 2 meter height, very large triaxial test cells are also available nowadays. So in this particularly what we do is that the sample is actually prepared under either from the disturbed or undisturbed conditions, or remolded sample is actually prepared, or undisturbed sample is actually placed, and the sample sizes are such that the from the different sampler tubes we can collect the samplers and then preserve the original soil fabric and original preserve the degree of the disturbance, and so that in situ shear strength parameters, directly the samples which are actually collected from the borehole investigations, the same thing can be used here. And with that when you perform and different types of drainage conditions we are able to maintain, then there is a possibility that you will be able to determine the strength parameters suiting to the field conditions depending upon the type of the the stress test which you are conducting can be adopted. So this is the typical component of a triaxial test, where you actually have got a sample and a chamber in which what you have is that the confinement is actually provided in the form of filling the water. So initially when the sample is actually placed, and as an interface there is a membrane which is actually placed called rubber membrane, and then the load cell which is actually placed here, this is the pork or loading ram, and inside is actually filled with water, and this water is actually pressurized to different pressures, and when we are actually having sigma 3.1, sigma 3.2 and sigma 3.3, different cell pressures are actually applied. So, and then for different cell pressures when it is actually applied, initially the pressures are actually uniform, and then in order to simulate the increase in the load, what actually happens is that you apply deviator stress. So with sigma 1 is equal to sigma 3 plus sigma 3 plus P by A, and that is actually what we get is that sigma 1 is equal to sigma 3 plus P by A, and what we regard as sigma 1 minus sigma 3 as the deviator stress, the difference between major principal stress sigma 1 minus sigma 3 is actually called as the the deviator stress. So we get deviator stress versus axial strain, and that is in case when you are actually doing a compression test. So sometimes we can actually have controls on the you can actually arrest the movement of water, so that means that no volume change is actually allowed. Then in that case we can simulate undrained conditions, and we can also measure what is the pore water pressure upon shear when the drainage is actually not limited in a saturated sample. And when suppose if you are trying to drain the water and subject it to shearing condition, then what will happen is that the the consolidated drained conditions or drained parameters are obtained. So, in the next lecture we will try to look into further about the triaxial tests, and further we will try to look into the other aspects of the interpretation of the triaxial test results.